This is a chi-squared table. Like the t-distributions, chi-squared is based on degrees of freedom. Here's a nice way to introduce chi-squared. Let's suppose we're doing a z-test on the proportion of tails flipped by a suspicious coin. We're simply testing to see if the coin is fair, that the proportion of tails is equal to 0.5. Potato Head here flipped the coin 100 times, knocking his ear off twice and poking his eye out once, but he got the job done. In all, there were 40 tails and 60 heads tossed. And when we say 60 heads were tossed, not one of those was a potato head. No toys were harmed in the making of this video. What about the ears and the eye? Much. No toys were harmed much. Here's what it looks like if we're going to use the calculator. With a 1 proportion z-test, the p-hat was 0.4, the z-score was -2, and the p-value is 0.0455. In this case, the chi-square distribution is the standard normal z-distribution squared. So picture the left half of this distribution with negative z-scores, all squared and thus swung over to the positive chi-squared values, and this right-hand side of the positive z-scores also squared and added to the same squared values from the left side. The chi-square looks like this. It's skewed right with the highest probabilities near a z-score of 0 being at the mean or near the mean. Our result of z equals -2 is squared and becomes chi-squared equals 4, and the p-value is exactly the same. Here's how the chi-squared test statistic is calculated. Instead of proportions, it deals with binomial successes. We've seen the relationship between proportions and binomial before. O is the observed count in a cell, E is the expected count in a cell. If the null is true and we flip 100 coins, we expect 50 tails and 50 heads. We now square the difference between the observed and expected counts and divide each result by the expected count so that the differences squared are all relative to the expected counts. In this case, our chi-squared test statistic is 4.0. We have 1 degree of freedom because the number of heads and tails in 100 flips are dependent of one another. Once we knew that we had 40 tails, there was only one possibility for heads flipped, knowing we flipped 100 times. Our degree of freedom is for the number of tails. If we flipped another 100 times and got 54 tails, there's no freedom from the number of heads. It must be 46. The z-test on this proportion would yield a z-score of 0.8 and the p-value of 0.4237. Running the chi-squared test on the same data squares the z-score, yielding a chi-squared test statistic of 0.64, and it returns the same exact p-value. This gives you the basic relationship between z and chi-squared with 1 degree of freedom. The chi-squared test is always the two-tailed alternative. Recall that the critical z-score of plus or minus 1.96 traps a combined 5% on the tails in a 1 proportion z-test. 1.96 squared is 3.8416, and this is the critical chi-squared trapping 0.05 beyond it. We move to more degrees of freedom in chi-squared distributions on the next video.